Despite not involving a huge amount of theory, this video is actually going to cover both of the first two lessons in the DIG module. This is because the second lesson is primarily going to be a practical to explore the theory that's covered in the first lesson. And what we're going to be looking at is this material property known as resistivity, which is very closely linked to resistance. And just to apply a little bit of context, we're first going to talk about grouping material properties into two classes, being intensive or being extensive. So intensive material properties are those which have no dependence on the size or shape of a sample of material. So examples being density and Young's modulus. These are a property which a material has and doesn't depend at all upon the shape of a particular sample we're looking at. This is in contrast to extensive material properties which do depend on the shape. So we can draw analogies here. So mass would be the extensive equivalent of density. So the intensive property of density, when we start to factor in the size and shape of the material, we're now looking at the mass of a sample. And similarly, Young's modulus, we factor in the size and shape, and suddenly we're talking about stiffness. Now resistance does depend on the size and shape of material. We saw that previously when we've had a look at the equation I equals NQVA. So yes, it's current rather than resistance, but we can see that all else being equal, if we vary the area, we're going to vary the current. So if we have a look at Ohm's law, V equals IR, then for all else being equal, if we vary the current, we must be talking about a variance in the resistance. So varying the area, varying the size and shape is affecting the resistance of our material. So resistance is an extensive material. So just like when we were talking about stiffness, we said, can we come up with some sort of intensive version that is the Young's modulus, and that's what resistivity is. So resistivity is an intensive property of a material, which is a way of describing its resistivity. And the equation we use to work it out is this one. So rho, the resistivity, is Ra over L. So if we clear this screen off a bit, then what it's saying is if we're presented with some piece of wire or some material, it might be cylindrical or it might be some other cross-section, and it has a cross-sectional area of A and a length of L, and the resistivity of this material is rho, then if we wanted to find out what's the resistance of this portion, so if we imagine connecting a voltmeter to the ends and measuring the current passing through it to take the ratio to get the resistance, we would relate them by the rho equals Ra over L, or equivalently we could write R equals rho L over A. So we can see that for a given resistivity, the longer a wire is, the larger the resistance is going to be. The larger the cross-sectional area, the lower the resistance is going to be. So if we've got two wires made out of exactly the same material, one's short and fat and one's long and thin, then the short and fat one will have a lower resistance than the one that's long and thin. And in fact we can quantify this. So if we had two wires with the same area and one had twice the length of the other, then that would have twice the resistivity. If we had one which was twice the area than the other, that would have half the resistance. If we were looking at a circular cross-section and one had twice the radius, then that's going to result in 4 times larger cross-sectional area, which would mean a quarter of the resistance. So that's resistivity. It's the way of measuring the resistance of a material without having to worry about its size and shape, just like Young's modulus back in the first term was a way of measuring the stiffness of a material without having to worry about its size and shape. The units, it is the resistivity is Ra over L, so ohms, meters squared over meters, so ohm meters is how we describe it. So that's that bit, and we can see it put into action to describe, to explain the way in which we add resistors in series and parallel. So looking back into SPC now. So when we've got multiple resistors in series, we can see that effectively what we've done is, if we imagine just for a moment that all of these are the same, we've taken several of these and we've tagged them end on end, which leaves the cross-sectional area the same, but the length has been increased proportionally. So we can see that the resistance is going to go linearly with L, and so we see resistance proportional to L, and so we say that the total resistance is the sum of all of the resistances. You can imagine the resistance, if this was 1 ohm and this was 2 ohms, then maybe this one's twice the length of that one, so we just add it all up and that leads us to that. When we're looking in parallel, we can imagine something slightly different, where rather than having our portions of material tacked on end on end, so this one, then one over here, one back over here, what we do is we've lined them up in parallel. Now the lengths are all the same, but the cross-sectional area, the total cross-sectional area, is going to increase. So if we imagine this one had some cross-sectional area, and then we added a bit more cross-sectional area here and a bit more cross-sectional area here, you can see what we're doing is we're increasing the cross-sectional area, and a higher cross-sectional area means a lower resistance, so resistance and cross-sectional area are inversely proportional. And so this is why the resistance falls when we combine a whole bunch of resistors in parallel instead of series. So that's it, relatively straightforward for this one. We're just introducing the concept of this resistivity and this equation which allows us to use this resistivity, and if we know the length and cross-sectional area of a sample, we can determine its total resistance, or if we know any three of these, we can work out the others. So if we knew the resistance, resistivity and length, we could find the cross-sectional area, for example. And this is what we call an intrinsic material property compared to the resistance being an extrinsic material property. And just briefly how we can use this to explain how resistors combine in parallel and series a little bit.